Now let's continue the discussion on this graph of a transitive relation R5. So we have seen that if you just look at this connected component, then there is a node 5 and that has no incoming edge. So node 5 has no incoming edge, but node 5 is is related to every other node in this graph, because there is a directed edge from 5 to every other node. Okay, and this is because of the transitivity property. Some of the edges from 5 are to satisfy the transitive constants also, because what is the other node out of this remaining 4? What are the nodes that has only one incoming edge? That is 2, and the incoming edge is from 5. Now if you look at 2 also, if you look at 2, then 2 is not related to 5, but apart from 5 it is related to every other node, and this is also because of transitivity. Because when you are let's say adding edges incrementally, uh, so let's say I do not have this edge and this edge right now. Let's say you do not initially I have only one edge from 5 to 2, and one is reflexive. Means there is a one is related to itself, self loop on one. So there is only one edge from 5 to 2, and now you connect 2 to 1, and now because of this edge you have to add this edge. So this edge is, you can say, this is an implied edge. The moment this edge is added, this edge is implied automatically, because the relation is has to be a transitive. So this is one transitive edge, you can say. This edge from 5 to 1 is transitive edge. Similarly, from 1, when you add 1 to 3, okay, now the moment this directed edge is added, because 2 is related to 1, so 2, there has to be one edge from 2 to 3 also for transitivity to hold. So this is a edge, you can say this is a transitive edge. Okay, similarly, I don't know if this is a thing or this is a term called transitive edge or not, but let's say this is a transitive edge. uh, Similarly, this edge from 1 to 3 also, 5 to 3 also, you have to connect 5 to 3 also, because 5 is related to 1, 1 is related to 3, so 5 must be related to 3. So this is another transitive edge. Okay, you understand that any node in the connected component, if there is no incoming edge to it from any other node, then there has to be an edge from this node to that node. Either it be a directed edge because of some incrementally adding an edge, or is a directed edge because of the transitive condition, transitive constraint, to satisfy the transitive constraint. For example, you incrementally add an edge from 5 to 2, and there is no other edges. Now the moment you add an edge from 2 to 1, means you are incrementally adding another ordered pair in your relation. So the moment you add this edge automatically has to be added to satisfy the transitivity. Understand? So you can say that as the number of nodes will increase, you know, the number of edges will increase, but many of them would be transitive edge. So just if you do not have transitive edges in place also, means you can just have a something like this: 5 and 5 to 2 is connected, let's say, and then 2 is connected with 1. I mean, there are all vertices in here. Every vertex is there. Then you can just leave it like this with an added information that the relation is transitive. This is the added information. What is the added information? That relation is transitive. If you say that the relation is transitive, and this is the incomplete graph, but other edges can be deduced from it, then you can easily find out what are the other ordered pairs, because you just have to list the transitive edge. So from 5 to 2 there is an edge. You see there is no incoming edge to 5, and there is an incoming edge to 2. It means that whoever 2 is going to be connected to, you have to connect 5 to that also. So from 2 to 1 there is an edge, so there is a transitive edge automatically follows from this edge. Similarly, now once you have connected 5 with 2, now whatever connected component that is going to come in the from here in the remaining nodes, 5 has to be connected to 2. Means from 2, wherever you can reach to, whatever nodes you can reach to, you have to have a direct edge from 5 uh, to confirm the transitivity. Let's say if I am going to connect 5 with 7, if I am going to connect 5 with 7, let's say I connect 5 with 7, then do I need any, means because of adding this edge, do you need to add any other edge to confirm the transitivity property? No. The reason being that there is no incoming edge to 5. There is no incoming edge to 5, so any edge that you have added, there is no transitive dependency of any node. If there is no incoming edge to 5, means that there is no edge, there is no node that is there from which you need a directed edge to 7 also. But if you look at 2, if you look at 2, okay, let's say this edge is not here now, but if you add an edge from 2 to 7, now you look at the, you look at 2, that if there is any incoming edge to 2 or not. Yes, there is an incoming edge to 2. It means from whichever node it is coming, from whichever node the incoming edge is there, if 2 is connected to 7, then there has to be follow a transitive edge from 5 to 7 also. You got it? Here you can see in this graph all edges are unidirectional. When it comes to two distinct nodes, every edge is unidirectional. Let me take a case where 5 and 2, 5 is related to 2 and 2 is related to 5. Okay, let me take a bidirectional case. So look at here, let me make it a bidirectional. If I make it a bidirectional, if I make it bidirectional, now when you add 5 to 7, now there is an incoming edge to 5 from 2. So the moment you add 5 to 7, a transitive edge from 2 follows. A transitive edge from 5 to from 2 should also follow 7. Similarly, because this is bidirectional, let's say if I add an edge 2 to 6, 2 to 6, if I add one edge 2 to 6, which is basically I am adding one more ordered pair 2 to 6, 2 and comma 6, then because there is an incoming edge from 5 to 2, so there has to be one edge, as because of this edge you have to have this edge which is a transitive edge. So this was the case when you have a bidirectional one edge which is bidirection, but here all of the edges is unidirectional. So you can say that this transitive relation is also antisymmetric relation. This R5 between any two nodes, the directed edge is a unidirection. So in that case, this is an antisymmetric relation, and this is also a transitive relation. And there is a special property of transitive relation, the combination of transitive and antisymmetric. What is that? You can see there's an order. There is an order. What is that order? The order is that let me show you the order. The order that I'm going to show is not, will not be there in case there is any bidirection edge. So I'm specifically talking about transitive and symmetric relation, transitive and antisymmetric relation. Specifically, I'm talking about the one property of transitive and antisymmetric. We will find out that we will add reflexive relate the combination to have the reflexive relation also. But wait for a minute. Let me erase this. If you see this, what is the order that I'm talking about? The order is this: 5 has no incoming edge, so 5, and then look at 2. There is only one incoming edge to 2, so then 2. Okay, there's another on. There are two incoming edge to 1, so then 1 will be there. There is 3 incoming edge to 3, so then 3 will be here. There is 4 incoming edge to 4, so then there is 4 here. This is one order. There is an order in the connected component. Okay, I'm not talking about there is an order in all the nodes. I mean, 6 and 7 are two different components, but if you look at only one component, these connected component, so there are three components. Okay, and there is order in, let's say this is another component and this is another component. These are the three components, and this is the order of the connected component. What is the order? 5, then 2, then 1. What this order means? This order means that this 5 is going to be related with every other node. This 2 is not going to be related with 5, but 2 is related with every other node. Then 1 is not related to any in the left side, left to it, but 1 is related to 3 and 4. 3 is not related to whatever comes before it in this order, 1, 2, and 5, but 3 is related to 4, and then 4 is not related to any of it, but every one of them is related to 4. This is the order that I am talking about. To add to this, we can say that when your transitive relation is antisymmetric also, when your transitive relation is antisymmetric also, there is an order in the connected component. There is order in the connected components, in the nodes of a connected component. So when you write like this, you know that 5 is related to 2, 5 is related to 1, 5 is related to 3, 5 is related to 4, 2 is related to 1, 2 is related to 3, 2 is related to 4, and then 1 is related to 3, 1 is related to 4, and then 3 is related to 4, and that's it. This is one connected component, and this is another connected component, and this is another connected component. Okay, let's say if I connect this 6 to 7 also. Let's say I connect this 6 to 7. Now this is still a transitive relationship. So if you connect 6 and 7, then you can write this connected component now as 6 comma 7, 6 and 7. In this order you can write it, where 6 will be related to 7. When I add a further to a relation that is transitive and symmetric, if I add a further condition that every element is related to itself, then this combination as a whole will become a relation that is transitive, antisymmetric, and reflexive. And then this type of relation will be called as partial order. Then I can give a symbol between the elements, which is like this symbol. This is a symbolic, this is not less than equal to, but this is a symbol of, that this relation is a partial order relation. So what is a partial order relation? What is a partial order relation? Why it is called partial order relation? Because there is not, there is order in some parts of the nodes which are connected component. So for these nodes, not all nodes, means there is no order, there is no relationship between 6 and 7 and any of the nodes here, but within 6 and 7 there is an order, that 6 is relative to 7. Similarly, within these set of nodes there is an order, that 5 is related to every other node, 2 is related to 1 3 and 4, 1 is related to 3 and 4, 3 is related to 4. And when you are giving, and when you are adding a further condition that okay, my transitive and antisymmetric relation is also reflexive, then what will happen is that you can define a new type of relation which is called partial order, which you can give it a symbol like this, which means to say that your that 5 is something like this. So as you can see, this is not a less than equal to in a general, in normal scenarios that you know of, because 5 is not less than 2. This is basically a symbol for partial order relation, which means to say that basically if your relation R is partial order, then 5 is related to every other node, 2 1 3 and 4. Then 2 is not related to 5, but 2 is related to 1 3 and 4. 1 is not related to 2 or 5, but 1 is related to 3 and 4. So there is an order, and you can write the nodes in that order. And this is called partial order because it is not, there is not an order in all the nodes of the on all the nodes or on all the elements of A, but they are, but to those elements of A which are part of one connected component. Okay. So what is a partial order relation? A partial order relation is a relation that is transitive, a relation that is transitive, that is antisymmetric, and reflexive. So in any partial order relation, any partial order relation that has this is the graph of that partial order relation. And as I have already shown you that many of the edges in this graph are just implied edges. So what we will do, that a partial order relation is, the graph of a partial order relation is represented by something called as Hasse diagram or Hasse diagram. That's what I used to pronounce. Hasse diagram. In the Hasse diagram, what we do is we do not have the transitive edges because it is implied. You know. Uh, so if I have to draw the Hasse diagram of, let's say this R5 is, if this R5 is partial order relation, if this R5 is partial order relation, then the graph of this relation, this is all okay, but you have to add another set of edges, which is for the reflexive part. So 5 is related to 5, 2 is related to 2, 4 is related to 4, 3 is related to 3, 1 is related to 1. Now, as you can see, these reflexive edges and the edges for which I use a term called transitive edge, those edges are implied. So in Hasse diagram, we do not have those edges. The edges that can be implied from the transitive property or the edges that can be implied from the reflexive property, we won't have those edges in my graph, because as the number of nodes will increase, the edges will also increase, and it will make the graph complex in look, and we don't want that. We want a beautiful graph. So we won't have the transitive edges unnecessary. We won't have reflexive edges in our Hasse diagram. This is two things. And third thing is that, just like I have shown you the order, I have written it in the horizontal manner. There will be an order in your Hasse diagram, which is that your nodes will be in the vertical direction. Draw the Hasse diagram for this. Hasse diagram, the corresponding Hasse diagram for this partial order relation R5. So the Hasse diagram is, you have 5. 5 is related to 2. Okay. And then 2 is related to 1. 1 is related to 3, and 3 is related to 4. And 3 is related to 4. So you just go into this direction. Okay, 5 is related to 2, 2 is related to 1, 1 is related to 3, 3 is related to 4. And that's it. This is your Hasse diagram. Of course, 5 is related to 5, but we will not include these edges because of the reflexivity. Of course, 5 is related to 1, but this is a transitive edge, so I am not adding that also, because these edges are implied because of the fact that R5 is transitive. And then you have 6 and 7, that is completely different component. So you have 6 here and then 7. Okay, that's it. That's it for today. And in the next video, we will solve some problems related to, we will revisit reflexive, symmetric, antisymmetric, asymmetric, transitive. We will solve some problems related to that. And after that, we will again come back to partial order relation and read about it in depth. Thank you very much.